coming to the energy session of the Alumni Weekend. I'm James Marrow. The other speakers we have this afternoon are Nick Eyre and Brenda Boardman. We're going to introduce ourselves as we go through. The aim is we'll all talk for about 10-15 minutes on what interests us in energy, and the idea is after that to have a fairly open discussion. So we do welcome you to note down questions and come back at us with questions. We're going to go through all three talks first and then have a good question session at the end. Okay, so just introduce myself. I've recently joined Oxford. I'm a member of the Oxford Martin School and also the Department of Materials. And my research area is cracks. I break things and I study how things break. And that has quite an importance in the energy industry. I'm not going to cover that in the talk I'm going to run through now. What I'm going to talk about is where does our energy come from and what are the drivers in energy. And it's some material I put together for my first lecture course, which I did to the undergraduates. And I had to do a lot of reading, a lot of thinking. I actually learned quite a few things I didn't really know. So hopefully there'll be some interesting things here. I'm going to cover, first of all, what do we use all this energy for? Everyone's talking about energy and CO2 and so on. So let's think, what do we use energy for? And where does our energy come from? There's a lot of focus on electricity because that's one of the most obvious uses of energy. And I want to dig into that a little bit. Then talk about some of the things which drive energy supply and drive the strategy for energy supply, which I touched on here, and some of my conclusions. But the idea is to have an open talk. The sun's there because ultimately that's where our energy comes from. Nuclear energy, okay, that comes from other suns, but ultimately our energy does come from the suns. So I put that there to remind ourselves. We use an awful lot of energy, and we get it from all sorts of different sources, and I'm going a bit more depth about what these sources are. We use an awful lot. So lots of different forecasts, but all of them show a rising trend. Now what's going to happen in the future, which way that trend will go, is going to be interesting, but currently trends are rising. I'm going to be throwing in these slides lots of different units. That's one of the big problems when you start digging into energy, what units to have. The default one I'm tending to use is millions of tons of oil, okay? And we use an awful lot. Every year, around about now, we use about 12,000 million tons of oil. I invite you to think how big a volume that is, how many tons of oil you fit inside this lecture theatre. So what do we use it for? Loads of stuff, okay? Mostly moving things, heating things, and making things. A little bit for powering widgets like this, okay, and heating and so on. And we lose a bit of it, particularly electricity, but we use an awful lot. This is the UK per capita consumption. I'll show some figures, and I'm sure those will later on figures. The book I recommend is the book on sustainable energy by David Mackay. It's a very reasonable book, and some of the figures and information will come from that text. Now, electricity, because we all think about electricity, is actually a fairly small fraction of the energy we use. These are the figures for the world consumption, and some of us use more than others. The blue figure is the world average. UK is higher than world average, the US is well above world average, and China is well below at the moment. But there's some interesting trends within those data, which I'm sure Nick and Brenda will touch on. What do we use these different forms of energy for? Let's look at electricity. What do we use electricity for? Well, currently, we don't use very much of it for transport. We use most of it within industry and quite a lot within our homes, running buildings, things like that. If we want to reduce the amount of electricity we use, we've got to focus into these particular areas. Where do we get our electricity from? So focus on electricity at the moment, which remember is a fairly small fraction of all the energy we use. Where do we get most of it from? We get it mostly from burning fossil fuels, of which coal and gas and oil are quite significant. And what's likely to happen in the future? Again, there are forecasts, but these are forecasts from fairly reliable sources. Expectations in the next few decades is we will continue to use a lot of oil and coal and gas, and the amounts we will use will increase. And just to summarise what we've talked about there, okay, we use an awful lot of energy, about 12,000 million tonnes of oil equivalent. Where does it come from? About two-thirds, less than two-thirds oil and gas, about less than a third from coal. We use it mostly for heating and moving stuff, and we use some of it for electricity. And electricity is, as I've said earlier, a fairly small amount, about 12% or thereabouts. And where does that come from? Mostly comes from coal and gas. If we're going to change the amount of energy we use, we've got to target these different areas. It's no good just focusing on electricity for lighting, for heating, if you want to shift the whole figure. It's important, it's worthwhile doing, but there's a big lump of energy that we use. So what covers, or what changes, or what drives our energy supply strategy? Well, one key thing, of course, is security of resources. We like to be sure the lights go on when we press the switch. We like to be sure we'll be heated in the winter. So let's look at our major fuel sources. What do we use those for? If we lose that source of energy, what's it going to impact on? If we want to change the effects of that energy, what are we going to do? Well, oil, okay, fairly obvious. We use oil mostly for transportation. Okay? Fairly important in industry, but mostly use it for moving stuff because oil is a very dense energy source. It's easily transportable, easily moved, easily carried with us in a vehicle. Where does it come from? Fairly obviously, certain countries are quite important. You've got Saudi Arabia at the top, important for oil, but at the rate we're using, it's going to run out in about 80 years if you believe these figures. Canada, fairly high figure, that's largely the oil shales, things like that. So as you move down, look at the list of countries. They're all quite important in terms of politics and geostability. That's why oil is very, very important. What about gas? Gas you normally find where we find oil. And as you might expect, we use gas mostly for heating. We don't use it for transport in a serious amount, and so on. So gas also extremely important alongside with oil. Where does gas come from? Well, gas, again, generally comes from the places we get our oil from. And geography and world politics, therefore, very important in oil and gas supply. If you live close to the border with Russia, you might be worried about the pipelines, things like that, because if you're reliant on gas, those pipelines are easily turned off. What about coal? Coal's a little bit more interesting. Coal, mostly used for heating and electricity generation. Coal is not that transportable. In fact, it's mostly used where it is mined. We do transport coal around the world, but it's mostly used where it's mined. And if we want to see why the forecasts show that coal will continue to be important, we just look at where is the coal. You might be able to read these figures, because the slide's a bit small, but over here on the left, find a pointer. You've got the USA, black figure is coal. Here you've got the former USSR. Here you've got China. Here you've got India. These are the countries with very, very large coal reserves. It would be surprising if they don't continue to use that coal. And if we look at what's likely to happen in terms of where the coal is and where countries are developing, we can expect coal use to increase substantially in the future. And that will have some interesting effects. Touching on nuclear, because of course nuclear is very important in the current debate. Nuclear's had a heyday back in the sort of 60s and 70s. We built an awful lot of nuclear power stations, and around the world there's about 440-ish power stations, mostly in America and France. They're getting old. Yeah? This is basically a plot of how old they are. And most nuclear power stations last about 30, 40 years. There are plans for them making it lasting longer. People talk about 60 years, 80-year lifetimes, but realistically the plants we have now will stop operating after 30, 40 years. So quite a few of them are going to shut down next 10, 15 years. So nuclear is either going to have a brief flurry and be finished, or there'll be some kind of renaissance and we'll build some more. And it's very interesting to know or to think about what we might build in the future. But nuclear is not that important. Yeah? We use it to generate electricity, and electricity is a fairly small amount of the energy we use. So it's not going to solve the problem. These are forecasts of what you might expect to build in time in terms of nuclear power stations. The pale green is the most optimistic predictions. The dark green is the lower end of the predictions, and the blue is basically what we've done in the past. And that amount of energy generation is not very significant compared to what we need. So just to summarize what I've said, oil and gas, important strategic. We know that. It's because we use a lot of them very much. Coal is less strategic because we tend not to ship it around a lot, but where the coal is, it's probably going to be used. And coal and oil and gas are all greenhouse generating. So what's going to happen in the future? Well, we know the world is going to change. Where do we use our energy? Well, this is a NASA shot of the Earth one night, and you can see where we use the energy. It's mostly in the developed world. But we know where the world is developing, and we know what they would like to do. They deserve the lifestyle that we have. So what's going to happen to energy needs? What's going to happen to population? Whatever statistics you want to take, populations tend to grow, have been growing. And this is a rather interesting figure. I don't know if you read the text. Again, this is the figure from McKay. It's basically a plot of GDP per head against the amount of energy we use. And by and large, as we get richer, we use more energy. And we can therefore expect to use more energy in the future as our population grows, as our countries become richer. Behind all this, of course, is climate change. We haven't really got time to go into details of climate change. We can talk about it in the conversation. But it's interesting to look at where do we produce CO2 or greenhouse gases. And as you might expect, it goes with where we produce and use energy. The USA produces an awful lot of greenhouse gases per capita. The less developed countries produce less. But that'll change. This graph will shift towards the left. And where do greenhouse gases come from? Well, most of it is energy. Some of it's from methane and agricultural work and things like that. Some of it's nitrous oxides, but by and large, it's energy is the driver for CO2. And yeah, we know this, but we don't do very much about it, that energy use is going to increase, and most of energy comes from fossil fuels. Fossil fuels, we've got a lot of them still, so we'll probably carry on using them unless we change what we're doing. So, 21st century, we have the time to make some choices. There are things we can do. Do we move towards a carbon-free society? Well, we know that's expensive. It's a choice we have to make. How much are we prepared as a society to pay to move towards a carbon-free society? Do we go part way? Do we compromise? Is it going to be enough? What consequences can we live with? Do we say, let's keep on producing the CO2 and put it somewhere? Yeah? There are ideas on that. How far evolved are they? Are they really practical for the amount of energy which we will continue to use in the future? Or do we do nothing? There are those who believe that CO2 emissions and so on are having no real effect. It's an interesting question. We can talk about that. But one day, fossil fuels will run out, guaranteed. A few generations more, we will run out. We will use them all, and we'll have to make some serious choices. So, concluding the main things I want to say, we will need more energy in the future. Let's do something about it. Where energy is, how available it is very important in global politics. We need long-term energy supplies, either sustainable or they might have to increase, depending on what choices we make. And there is real pressure to develop energy sources which do reduce the amount of CO2 that we emit. And where do we target? Where should we target? Well, look at where most of the energy is used, and energy produces CO2. It's transport and heating. If you will bear with me just for 2 minutes, I'll just touch on this. What are our choices for producing energy in the future? These are the kind of things which are available to us. Up in the left, and we drove in here, we'll probably come past Didcot, very large power station. We've got wind, we've got Sizewell B, nuclear power station, all the various forms. And what I tried to indicate on this is roughly how much energy you get from each of these. Sizewell's quite big, it produces 3.5 gigawatts of energy. Fusion plants, if and when we build them, the expected size is around about 1 gigawatt, and most big power stations are around about 1 gigawatt. Renewables are much smaller. They do tend to be much smaller. And if we look at what you could produce in terms of gigawatts from various types of power source, this is the maximum energy. Over on the left, we've got the Severn barrage, if you built the Severn barrage. Then we've got Didcot, typical big coal power station, Sizewell, typical nuclear station, typical fusion. And we've then got typical sizes of wind or solar power stations or wave power stations, the expected sizes and so on. Now, of course, these aren't used all the time. And if we look at availability, which is described as load factor, basically how much of the time in a year you can expect the power station to be operating. Tidal systems, of course, only work when the tide's running, so they have a low availability. Most big power stations, coal, nuclear and so on, are available around about 2/3 of the time. The other third of the time you're doing maintenance, they're shut down, they've got problems. Most renewables, based on the figures available, are around about 1/4 of the time, okay? And some others are a bit lower. If, out of interest, you multiply those two together, that's how much energy you might expect to produce per year from these typical types of power station. Now we use at the moment, this electricity, about 6 megawatt hours per year per person. To put into context, take the population of various places. Outer Hebrides, typical population, Oxford, Oxfordshire and London. How many power stations do we need to power these places at our current consumption? Well, skip that. What it shows you is most of the renewables at that size scale will be fine for smaller communities. If we want to power large communities, we've got to do something very, very different in terms of the scale of these renewables. Most big power stations are around about big enough to provide power to a typical city. London needs Didcot, basically. if we're going to replace these power stations, these fossil power stations, with other forms, we're going to need an awful lot of them if we continue using energy at the rate we are doing so. Last point is how much CO2 do we produce per kilowatt hour. So in a certain amount of energy, how much CO2 do we produce? These are figures from recent analysis, and they show, as you might expect, that wind, hydro, renewables are all very, very good. Oil, coal and gas, without any form of carbon sequestration, are really terrible. Note the scale is a logarithmic scale, so every single unit is a factor of 10. Nuclear, if you believe the data, is not brilliant, but it's not as bad as the others. And this is just showing the uncertainties within these data. And this is the kind of things people are battling with now, making choices. You know, we have to balance how much CO2 we produce against how much energy we use, and we have to make some guesses and estimates on what are the costs. And one cost is CO2. So that's just there to remind me that if you take an oil coal-powered power station, power London for a year, and look at the amount of CO2 and turn that CO2 into dry ice, it's a cube around about 300 meters cubed. That's the London Eye, little tiny blue thing. Okay, CO2 is big unless we do something about it. Okay, so what do we think? All I think we need to think about is what would have the if we take global warming as the thing we have to deal with, what will have the biggest effect over the next century? Changing the way we generate our energy or using less of it? How do we cost energy? Is it just pounds per gigawatt hour or lives lost, lives lost because of the form of energy we use? And as a country, what should we do in the 21st century to support our needs? Okay, and with that, apologise for going on for 5 minutes extra, but thank you very much. I'll pass on to Nick.
Thank you, James. I thought that was a great rapid tour around the energy industry and saves Brenda and myself having to do some of the same things, so thank you for that. Can everybody hear me? Yes, good. My name's Nick Eyre. I'm a Senior Research Fellow at the Environmental Change Institute, which, for those of you who've been away from Oxford for more than 20 years, is part of the School of Geography and Environment. I was both an undergraduate and a postgraduate here in the dim and distant past, but have worked in various bits of the energy industry before coming back here 4 years ago. And the various bits include the Atomic Energy Authority and the Energy Saving Trust, so quite a diverse span of energy background. My interests now are really in how people use energy and how public policy can affect that. But particularly in the context of the big problem we face this century that James has mentioned, which is climate change, and how to bring the Earth's carbon dioxide emissions back down to a sustainable level. So I make no apology for showing starting from a very similar place to James. That's global energy use by fuel. And I think the big picture is twofold. One, it's going up. Two, it's mainly fossil fuels, coal, oil and gas, the big three at the bottom. And the other point I would make is that it is a bit like an oil tanker, not just in the sense of it's got lots of oil in it, but that actually the mix changes very slowly. There's a lot of inertia in this system. So turning that pattern round in a 40-year period to, say, reduce global CO2 emissions by a factor 2 by 2050, which is the sort of number that people talk about to stabilise the climate, is a huge task. And I actually don't think it is a choice between using less energy and changing the sort of energy we use. I think all the work that's been done indicates we will need to do both. So, never put an equation in a talk early on is the advice, so I haven't, because the mathematicians amongst you will recognise that's an identity and not an equation. Carbon emissions are the product of the carbon to energy ratio, the energy to GDP ratio and GDP. So there's a very simple message. If you want GDP to keep going up and you want carbon emissions to go down, then you need to do something about either that C/E factor, the carbon ratio, which is essentially the fuel mix, or you need to do something about energy intensity, E/GDP, the energy ratio, which you can think of as being to do with the efficiency with which we use energy. We have to address both of those. If we don't, we won't succeed in having a livable planet, is the quick message. I'm going to focus now on the UK and focus more on what we can do. I just thought I would start by showing you what we've done in the last 35 years or so to the energy ratio and the carbon ratio. The carbon ratio has gone down by about 20% in that period of time. That's with a substantial nuclear program in the 70s. It's with a dash to North Sea gas in the 90s. And you can see that ratio is beginning to drift up a bit, despite the push for renewables in recent years. In contrast, the energy ratio, the energy efficiency of the economy, has improved by something like 60% over that period. And so it is a point that I like to make, that really the energy efficiency of the economy over the last 35 years has delivered 3 times as much carbon reduction as nuclear power, new renewables and the dash for gas put together. That actually surprises many people, even in the energy industry, that the figures are that stark. Now, I have to admit that the energy GDP ratio is partly influenced by the fact that we've exported much of our manufacturing industry to China and East Asia in that period, but actually a lot of it is also technical efficiency, improvement in the efficiency with which we use energy. So I think the big picture is our carbon targets are very tough. Most of you will know that the government is committed to an 80% reduction from 1990 levels by 2050. That's about a 75% reduction from now. Another bit of maths there. We've reduced our emissions 20%. We've got a target of 80%, but we still have another 75% to go. These things are multiplicative, not additive. So it's still very difficult, even though we've made some progress. As I said, we probably need to address the energy ratio and the carbon ratio, and historically we've done better at improving the energy ratio than the carbon ratio. I think it does mean that we not only need to think about those choices James showed at the end of his talk between all the different ways of supplying energy, but about how we use energy. And I say we quite deliberately because one of the slides James showed shows that half the energy used in this country now is by us directly, in homes, in private transport. The days when most energy was used by big industry in smokestacks have gone, and things are moving in the direction of energy being our responsibility. And it's that thinking that made us set us off on a short piece of research I'm going to describe very briefly about just a thought experiment. Can we change our lifestyles to a lower energy lifestyle that will help us deliver these ambitious targets? It's published by Earthscan. It's a chapter in that book, so you can all go out and buy that at Blackwell's afterwards if you want. And I'd like to give credit to my colleagues who worked on this, Christian Brand and Russell Laborie here, and Gillian Annabel Aberdeen and Neil Strachan at University College London. And this is indicative of the way that university research is going. We're working with people around the country and indeed increasingly around the world to address these sorts of questions. What are lifestyles? Well, suffice to say the social science literature has at least as many definitions as there are social scientists who work on lifestyles. A precise definition is difficult, but I think we know a lifestyle when we see one. That, I think you would agree, is not a low-energy lifestyle. I really love this slide. Firstly, it gets a laugh. But secondly, actually, it does make a serious point. What do we know about that lifestyle? Well, we know somebody is using a high-carbon, high-energy technology. But it's funny because they're using it in a way that, to this audience, looks singularly inappropriate. So there's a combination of technology and behaviour which somehow defines this lifestyle. And so lifestyles are influenced by technology, but they're also influenced by culture. Which country is that taken in? Yeah, it's so obvious that you probably recognise that within 1 second. So culture is really important. Now, culture can change. Culture does change. 20 years ago, young people used to walk down the street talking to each other. Now they walk down the street talking to other people who are not there. So things change over those sorts of decadal timescales, and presumably they can change in the way that we use energy. So in the lower energy lifestyle scenario, we were looking at and asking, well, what sorts of social change could encourage greater use of green technologies in buildings and personal transport, and different behavioural patterns in the way that they're used. Now, I say it's about us, but of course, people do not do these things in isolation from the rest of the world. So we also need to think about public policy, and we need to think about the infrastructures that encourage or discourage different ways of using energy. And if you think about the picture in the last slide, if the US had somewhat higher gas taxes and built decent public transport systems, then you might see less of that sort of behaviour. So there's an iteration between lifestyle and public policy. We made some hand-waving assumptions about lifestyle change. We looked at the sorts of lifestyle change that are feasible. If people cycle in Oxford and Amsterdam, then they can cycle in London and Leicester as well, those sorts of assumptions. So we looked at internal temperatures in houses that were at mid-1990 levels. We looked at not falling levels of appliance use, but just stabilisation. We looked at a world where people actually do insulate their houses, and where heating systems pick up some of the new technologies, biomass CHP heat pumps, and where solar energy use becomes more widespread. Now, none of those individual changes, you might think, well, they're a bit marginal. Individually, they all are a bit marginal. That's absolutely right. But if you accumulate them across 40 years, this is the sort of impact you can see. So the left-hand bar is energy use for heating UK homes in the year 2000, mainly gas. The second is what would happen by 2050 under a business as usual scenario. Still gas, but through gas boilers, condensing gas boilers rather than conventional boilers. And the third is this scenario where we looked at, and the striking things are twofold. One is the types of energy used are far more diverse. You've not only got gas, you've got electricity, you've got heat pumps, you've got some biomass fuels, you've got a lot of solar, you've got some combined heat and power. But perhaps more interestingly, the size of the bar is much smaller. That's partly because we assumed homes might be a little bit cooler than they are now, but it's mainly because we've insulated them properly. It's not rocket science, actually, some of this. We did the same sort of analysis for transport. My colleagues who work more on transport than I do looked at a whole series of ways in which we could maintain accessibility but reduce the amount of travel that's done, essentially. So more local services, people travelling at slower speeds, cities built more compactly, measures to encourage non-car free, less car use, how we could use ICT to increase the amounts of teleworking and teleshopping to do that, for example, and modest reductions in air travel from where we are now. Again, individually, none of those changes makes a lot of difference, but when we crunched the numbers, we found that it has three significant effects. One, the total distance travelled can begin to fall. Actually, it has begun to stabilise in this country now. Second, the modal choice can change from predominantly cars to still, yeah, a lot of cars, but more cycling and walking and more public transport. And thirdly, the way we power the vehicles can change. So electric vehicles can become dominant also with biofuels and some hydrogen fuels. And again, it's this combination of effects has the same sort of picture for energy demand in transport that we saw for household heating. Moving from a picture today dominated by petrol and diesel to a business as usual world in 2050 where it's just a bit more petrol and a bit more diesel, through to this hypothetical scenario where people's lifestyles change, where electricity, hydrogen, biodiesel take a much bigger share, but the dominant effect is that we actually use much less energy in transport whilst maintaining accessibility to the services that we all want and need. So my conclusions that I leave you to think about and hopefully challenge in the question and answer session are that really lifestyle change, because it combines technology and the way that technology is used, can be significant. We got those 50% reductions in energy use in homes and transport through a series of not particularly radical measures. And if those came about, they would, on their own, reduce UK CO2 emissions by 30%. 30% is quite a long way towards 80%, but it's nowhere near the whole way. So this agenda is not, on its own, a panacea at all. But I think it helps in one other critical way. When we calculated the cost of the energy system to do this, it came out at about £70 billion per year cheaper in 2050. That's about £2,000 a household. That's because energy is going to be quite expensive in 2050. So using less of it's quite a good idea economically. And also, to pick up on the point that James made about where oil and gas comes from, if we can use less oil and gas, then we are far less at the mercy of what one might consider to be less politically stable regimes than our own in the Middle East and Russia in particular. So that's where I'll leave you and hand over to Brenda, who's going to say more about what individuals can do, I hope.
I think so. Right, thank you very much. As you've understood from the previous two speakers, you've had the big picture from James, a big UK focus from Nick, and now I'm going to come down much more to the level of us at the household and how we use energy in our everyday lives. You can see my name is Brenda Boardman. I've now retired. I've been here at the University of Oxford since 1991, working in the Lower Carbon Futures Group, which is what Nick now heads. So, and all of that time, and from a bit before, I've focused on how we use energy, which was a slightly surprising thing for Oxford to find itself researching. But gradually they've got used to us working in the Environmental Change Institute on environmental issues. So we're quite happy to talk about the changes in Oxford as well as our own research interests. I'm doing the UK. I'm looking at the 50% of energy that we use as individuals, and particularly that part that we look at and use within our own homes. This is how we use it. And in terms of energy, 60% approximately goes on space heating, 20% in hot water. And those are the two that mainly use gas. And if, as Nick was talking about insulation levels, that will largely reduce your space heating. And if you put in a condensing boiler, that reduces both of those because they've got a more efficient use of gas. The remaining 20% that we use in lights and appliances is almost exclusively electricity. And very, very roughly, a fifth of that you use in lighting, a fifth in what they call the cold appliances, fridges and freezers, a fifth in how you use your washing machine, tumble dryer and dishwasher, a fifth in IT, home computers, TVs, sound systems, and a fifth for cooking. And that includes oddities like the microwave and the kettle. And I'm now just going to give you a bit more information, particularly in relationship to that 20% of electricity. And as James said, we frequently focus on electricity in many of our debates. The nuclear, the renewables, etc., are all electricity generating. I'm focusing a little bit on the electricity and how we use it. But before I do that, in the average household, I've just shown you very approximately the gas and electricity usage. They're not quite the boundaries, as I was saying, they're just sort of nearly there, but 75% of the energy we use is gas, and only 25% is electricity. But because we have to generate electricity in a power station, that makes it much more carbon intensive, because 2/3 of the energy in the traditional power stations is wasted in the cooling towers. So the carbon intensity of electricity is much greater. So if you were to divide your carbon emissions between gas and electricity, they're very nearly half. And for exactly the same reason, the cost is nearly half. Very interesting if when you return home and you look at your gas and electricity bills just to find out how much you pay on each and see whether my average numbers are at all appropriate for you. Because electricity is generated in power stations, and because those can be a completely different mixture of fuels, and because the people that supply that electricity to us, the Electricité de France, the Scottish Power, the RWE, whoever it is you buy yours from, they purchase different combinations of power generation and therefore sell you electricity with different types of carbon intensity because of the mixture. So what you've got here is, of the big six, and I've just picked out EDF and Scottish Power, as the cleanest in CO2 terms. And why is it clean? Because it uses a high degree of 2/3 as nuclear. Almost all of the big six have to use the same amount of renewables because they have an obligation. If you didn't want to buy nuclear and you bought Scottish Power, you would be buying something which is much more CO2 intensive, but you wouldn't be supporting the nuclear industry. The other four are in between. If you really worried about climate change and didn't like nuclear, you could go for something which is 100% renewables, like good energy, and that is no CO2 emissions and no nuclear. And that's the UK average along the bottom. You can switch. I mean, almost all of the debates about switch and others are along the lines of price. This information, and I've given you the website along the bottom, and it's not easy to find, but oh dear, sorry, I've gone back the wrong way. Here we go, electricityinfo.org, supplier data. You have to search for it. It's a bit more available these days, but you could switch on the basis of what electricity industry you want to support and the extent to which you want to begin to change the climate change impact of your actions through the electricity you purchase. Unfortunately, it is too little known about. The information is meant to be supplied to you once a year on the back of your bills or with your bills, but most people haven't noticed that. It may not even have been there. So one of the things that I would certainly suggest you do is you get a little bit more familiar than you possibly are with your own electricity consumption or gas consumption or both. So for instance, the average home in the UK uses 10 kilowatt hours of electricity per day just in lights and appliances. Obviously, if you're going to start using your electric immersion heater to heat up your hot water, it's going to be more than that. See if you can get it down to 5. The Boardman household has got down to 6. And we're about to go lower because we've got CFLs in all of our light fittings, compact fluorescent lamps, those sort of folded tube things, and we're now about to put in LEDs into a lot of them. Whether that will get us down to 5, I don't know. It's not easy, and it does involve a huge number of small choices and small actions, like turning the lights off. We're fairly manic about turning the lights off. But that's something you could do quite easily without involving capital expenditure. You don't have to transfer to LED lights. You can just think about how much you might be wasting turning off your standby, etc. One of the things that we've done at the University of Oxford is produce a thing called iMeasure, and there's some leaflets up the front about it. And iMeasure is an absolutely free way of joining up with a website and putting in every week your meter readings. You get a nice little email to remind you to do it, so it's not too difficult. And this is, again, the Boardman household. So what you can see is that across the whole year, and that's 14 months I've got there, our electricity consumption is remarkably similar. Gas consumption, however, is very much higher in the winter. And interestingly, it's 0 during the summer. We do not use gas during the summer. That's because we have solar. Oh, sorry, somebody's naughty. That's because we have solar panels on our roof that heat hot water. So we turn the gas boiler off. somewhere around April, May, and we turn it on. We haven't quite turned it on properly. If it was raining the other day, I put it on, but we still haven't put it on properly. And so somewhere around September, October. So we have zero gas because the sun is shining. As James said, that's an important thing. Now, I find these things absolutely fascinating. Whether you do is up to you, but it's quite a nice way of easily tracking, and that graph comes out of iMeasure. It requires you to keep your information going for a year. Just some of the things you can do. Those are the compact fluorescent lamps, and now what we're going to is light-emitting diodes, LEDs, and those reduced our consumption of electricity over the incandescents to about a quarter, and these get down to a tenth of the old incandescent. And there's some very good and attractive lighting coming up through those now. With your appliances, everybody, I hope, is familiar with those labels. This is on a fridge freezer, I think. One of the things that I want to point out is that just because it's an A+, doesn't necessarily mean it's low energy. This happened to be a rather big fridge freezer, and some of the ones that they're selling us these days, the double doors, etc., are extremely large. If they are that big, they're going to be using more energy, even if they're A+ or A++ in terms of labels. So you've got to be a little bit savvy about not being pushed by the manufacturers just to buy big ones, because that's what they'd like you to buy. Things like dishwashers and tumble dryers, try to use as little as possible. I know that it's not always sunny to put the clothes out, and sometimes it decides to rain while you're at work, which is very irritating, but use those as little as possible. This is actually a plasma TV. Plasma TVs use about 4 times more energy than a liquid crystal display, an LCD. So if you're going to buy one, think about it. And LCDs are going to go down in their electricity consumption. So there's various ways in which we can be careful about what we buy and how we use it. The other thing I was just going to mention in terms of general issues is the whole issue of fuel poverty. And that's one area I've worked on. I did my doctorate on it and have recently produced a second book. And I've got a flyer about that, which is the cover, as you can see. And again, they're here. Because the problem of people being unable to afford adequate warmth and energy services in their homes is growing. It's at least 1 in 5 of the households, if not 1 in 4 of the households at the moment. And with the present squeeze on incomes and the quite substantial price increases that are still being announced in fuel prices, we expect fuel poverty to go up, unfortunately, fairly fast. Now, those of you who've recently bought or moved into a new property will have seen the energy label that goes on the home. That's called the Energy Performance Certificate. It's this side here that I'm particularly referring to. And it labels every home, just like the fridge, just like your washing machine, just like your light bulb, from A good to G bad. And this is a fairly poor quality one. It's an F-rated property. Those are basically unhealthy. You shouldn't really be living in them. They're too expensive to heat for anything like a reasonable amount of money to a reasonable extent. If you're going to take, and that unfortunately is where half of the fuel poor live at the moment. If you were going to take a household out of fuel poverty, you'd have them in a home that was an A or B rated, because obviously the smaller your income, the less you've got as your 10% for fuel, and that means it's got to be super energy efficient. A brand new home today would be about a B. For climate change purposes, by the end of 2050, we all ought to be A, and absolutely at a minimum of B. So we all, every one of us, has a huge task if what we're going to do is improve the quality of our housing and reduce demand and to produce less carbon emissions. The fuel poor are fuel poor because they have a combination of low income and energy inefficient housing. The darker the colour, the greater the fuel poverty. This is fairly schematic. I'm not suggesting that half of the households in Britain are in fuel poverty yet, but half the households in Northern Ireland are. So they're thinking of changing the definition. It sort of happens with governments. What is really difficult, if you're on a low income, even if you're in a reasonably energy efficient home, it's extremely difficult to provide adequate energy services and enough warmth for the money that you've got in a home that is reasonably energy efficient in the UK at the moment. This is actual data, it's not what we would like it to be. If you're on a high income and in a poor quality home, you can afford to take yourself out of fuel poverty and to waste a lot of fuel. So fuel poverty is about this really difficult combination of social factors and housing factors and energy brought together. Part of the reason that within Lower Carbon Futures we like doing interdisciplinary work. With things like this, it's quite challenging. So just to bring together what are the synergies between fuel poverty and climate change, in the UK, the poorest people are concentrated in the worst housing. So if what we want to do is get rid of fuel poverty, we need to upgrade those homes to being super energy efficient and low carbon housing. And that will have an impact on our carbon emissions across the country. There is a legal obligation on the government, the Warm Homes and Energy Conservation Act 2000, which says that fuel poverty is to be eradicated, brackets as far as is reasonably practicable, and maybe everything is reasonably practicable if you wanted to by 2016. That would require, as I said, every household to have about a SAP of 81 to be an A or B rated property. That's 850,000 properties every year from now onwards. If what we want to do is insulate, double pun meant, are fuel poor from fuel price rises and being cold. And for climate change purposes, by 2050, because we've got 26 million households to deal with, we've got to raise them to a SAP of 100 at a rate of 650,000 a year. So dealing with fuel poverty is actually the sort of precursor to dealing with climate change. So there are quite a lot of issues. The only other thing I've put down here on the front is the executive summary from a report that I did called Home Truths for Friends of the Earth and the Cooperative Bank about how to get an 80% reduction in carbon emissions. 80% is not enough yet, but it's still some of the information that you might be interested in. Thank you.